Okay, in this video I'm going to pick up where we left off with the t-test analysis, and we're going to talk about one-way designs that are slightly more complicated. One-way designs still fall under the category of simple experiments in that they have one IV, but that IV has two or more levels. In this example, we're going to have three levels or three conditions that we're comparing. And I'll remind you that we can actually study t-tests using a one-way ANOVA with just two levels, but most often we'll just use t-tests for that, although it gives the exact same result. So the first one I'm going to do is to look at these vocabulary, these kids' vocabulary at these different time points, 18 months, 24 months, 36 months. And I want to look at that using a general linear model. So go to Analyze General Linear Model, and we're going to look at a repeated measures design. This is a little bit unique in that we have a within subjects factor. We have these different time points that we're looking at kids' vocabulary, and we want to see whether or not there are differences between 18 months, 24 months, 18 months, 36 months, and 24 months and 36 months. And so we have to come up with a name for that factor, and a simple one would just be time, because we're looking at vocabulary across these different time points. In this case, time has three levels, 1, 2, and 3, and so we put that in here, and then we click Add, and that's the variable that we're considering. So I'm going to go ahead and click Define, and here's where you put those data. You could bring them in one at a time. So these are just the things that we are, these are the means that we are comparing. And I want to say that the way in which your data are organized may help provide some information to you about how you're going to analyze it. Because if we had a data set that didn't have a measure that was being repeated across time, then that might give us an indication that the variables are actually between subjects. But here we can see that the same variable is being measured across multiple time points. So that tells us that this is a repeated measures. We're repeating the measures. It's within subjects. So that's what we put in here. I'll just go in here and see if there's anything I would like to look at. You can ask for plots, I suppose. We'll see what that looks like. I'm going to go ahead and click OK. All right, so this is the general linear model that we just conducted, and there are a lot of different tests that are being given to you. And the one that I would like for you to find is a test of the within subjects. So there's some tests for between subjects effects. We're not interested in that. We're interested in tests of within subjects effects. And we can actually see that here we get two different examples of tests. And so you might think about, well, which one is the one that I want? And we are actually going to stick to this box. This is the test of within subject effects, and it gives us the effect of time using different kinds of statistics here. So there's a lot of different names here, but you can see that the test statistics are all the same. That's the case for this example, but that might not be the case for other examples. So here, I just want to go through and see what all we have. It didn't give us the means automatically in the output, so let's generate those as well. I always like to look at the means. So this was from the previous test that we did in the t-test tutorial. I'm going to put the three means in our dependent list, and we're going to look at just the means to start. So we can see that the average vocabulary, we can see it's increasing over time, and it's increasing quickly over time, right? So from 18 months to 24 months, we get about a 45 word boost, but then vocabulary is almost 10 times as high in that next year, so it's growing much faster after that. And I want to get back to this idea if I can remember to do so. so here I want to look at this within subjects test to begin, and we can see I'm just going to have you guys, for the purposes of this class, look at when sphericity is assumed. This is assumption of ANOVA, and usually we assume that we've met this assumption. So this is the statistic that we are going to be reporting. The error is given to us down here, and that's important too when it comes time to report our degrees of freedom. So what are we testing with this statistic? Well, what we're testing is to see whether or not there are any differences in these three means across these 3 time points. And this significant test, we can see it's significant because the F value is huge and the P value is less than 0.001, means that at least one pair of these contrasts, one set of these means is different from the other. And in fact, because of the previous video, I know that these sets of means are already different, and these numbers are so much bigger that I can only assume that all of our means are going to be different from each other. But this t-test just tells you that one set of the means has a significant difference. So it doesn't tell you which ones. We need to do the follow-up tests on that in order to find out. So let's first write up this overall model. So I'm going to put this down here so we can see everything. I'm going to go right here. I'm going to say we examined kids' vocabulary at 18, 24, and 36 months, and observed significant difference across these time points. And now, because we're in a one-way ANOVA instead of a t-test, our test statistic is actually an F. So we go italicized, capital F, and then back to unitalicized, we would go parenthesis, and here we report the degrees of freedom. In an F, we get 2 degrees of freedom. We get the first one, which is K minus 1, where K equals the number of groups we have. So we have 3 groups, minus 1 equals 2. So that's where that 2 comes from. And then here, the error is where we get the other degree of freedom. So we get 1, 1, 8. So we separate it with a comma, and a space is here. Now a space equals, and it's 244.39, and we'll report the p-value as p is less than 0.001. Now we can start doing the follow-up test. So we know that overall there's some difference among these means. We just don't know where those differences are. And here we will go back to SPSS, and we're just going to get a bunch of comparisons of means. And these are all paired samples means, remember, because these are all within subjects. So we're going to compare 18 months with 24 months. The next set I'm going to compare 18 months with 36 months. And the final combination is 24 months to 36 months. I'm going to ask for all of those comparisons. And that's provided to us in an instant with this table here. So we went through this last time when we talked about t-tests, but we see all of the means at the different vocabulary points here. This table gives us a correlation, so we can see what the correlations are across these time points. And one of the things that we can note is that they're all positive correlations, but and they're all significant correlations. But one of the things we can see is that at 2 years and 3 years, those correlations are really strong. They're quite robust. This is a large effect. So the bigger the vocabulary a kid has at 2 years old, the larger the vocabulary they'll have at 24 months old as 36 months old. We can see that that correlation is here as well. So as early as 18 months, the vocabulary there corresponds to higher vocabulary at 3 years, but this effect is much larger. And I'm saying that, but I would just caution a little bit to say that that question of much larger is actually yet another statistic that we would want to test, right? So we would want to test whether or not this correlation of 0.48 is different than this correlation of 0.69. So we probably wouldn't want to say that this correlation is much larger, but we could say that this is a large effect and this is a medium effect, or a medium small effect. All right, so back to where we were looking at these t-tests, and we know that from the overall f-test was significant, and we want to know where these pairs of differences are. And we can see that 18 months to 24 months is a significant difference. 18 months to 36 months, obviously a huge significant difference there. And even comparing 2-year-olds to 3-year-olds, we have a significant difference there. So all of the pairwise comparisons are significant. So in order to write those up, we want to explain a little bit more. Follow-up, so we would say follow-up tests showed that kids' vocabulary, and we know that from the means, the pattern of means, that the vocabularies are always getting larger, just as we would expect. So we say follow-up tests showed that kids' vocabulary at 24 months of age was significantly greater than at 18 months of age. And then we put the t-test here. So where is that test? 18 months and 24 months is here, right? So we'll report that as t, and the degrees of freedom is 59 equals negative 24.41, and a p of less than 0.0001. You say kids also observed that kids had a much larger vocabulary at 36 compared to 24 months. And I'm writing this in a lot of different ways, mainly to show you, so from sentence to sentence, writing this in a lot of different ways to show you that there's no real right way to write it up. What we really go for in writing up statistics or any scientific writing is to just make sure that we're trying to be as clear as possible. So this comparison, oops, I wrote the wrong one. So this is useful. So this actually should be 15.14, and p is less than 0.01. Finally, kids' vocabulary was significantly smaller at 18 months than 36 months. That should be fairly obvious given the other significant effects so far that we reported. So we're going to go ahead and type that up anyway, though. So we like to be thorough and present all of the contrasts. Oops. 0.001. Okay, so we have all three of our contrasts presented here. And the next thing we want to do is to just go back in there and report some of the means. So we don't have to type all of the means a bunch of times. We just want to have each mean show up one time. So we reference 24 months twice. We don't have to type the mean here and type the mean here. We could just put it up here. And then when the person reads this, they already know the mean. So here, again, we do m in italics equals, and at 24 months, it's 58.47. And then standard deviation equals 14.53, like that. And I'm going to make this easy on myself. I'm just going to copy and paste this formatting, and I'm going to put that in here as well. Put a space here, and then that way I can just change the numbers. 13.42, and at 18 months it's 4.43. Okay, and the only other mean that we have to report is the 36 months mean. And the first time we make reference to that is here. So I'm going to go ahead and paste that in there, and then I'm going to update this number, 544.62. And the standard deviation on this is actually quite large. So you can also see that as their vocabularies as they're getting older, the differences among kids is also getting larger. We can tell that from the standard deviations, that the standard deviation is really quite large at 3 months, which is consistent, right? Vocabularies of kids and adults are probably very much more as people get older than when they're more similar to each other when they're young. Okay, so here we go. I have a little space separating here, but unfortunately I have two, so I'm just going back in there and cleaning up that space. And so this is how we write this up. We examined kids' vocabulary at 18, 24, and 36 months and observed a significant difference across these time points. Report the overall F test. Follow-up tests showed that kids' vocabulary at 24 months of age was significantly greater than at 18 months of age. So we have the means, we have the test statistics, so we can show that it's different. We also observed that kids had a much larger vocabulary at 36 compared to 24 months. And finally, kids' vocabulary was significantly smaller at 18 months than 36 months. Or you could flip that and you could say kids' vocabulary at 36 months was significantly larger than at 18 months. And here we don't have to put the means because we've already presented them here. Okay, so that's how we would write up this within subjects ANOVA. Finally, I want to show you what this would look like if we were going to do the between subjects ANOVA. I'm going to show you, I'm going to choose a variable where we have more than 2 groups, and I'm going to choose mom's education. So does the amount of education that your mom get predict your vocabulary at, we could choose any of these time points, 18 months, 24 months, 36 months, and I'll just choose 18 months for ease. Or you could do all of them, and that might be a good practice thing for you guys to do. So I'm going to get means, and actually here I'm going to go ahead and look at 18 months, and I'm going to put in mom's education. And I want the first mom's education, not the code, because the code only has 2 levels, 0 and 1. So let's look at those means. So you can see across these, whether or not a mom has a high school education, college education, graduate education, it does not matter. Their vocabularies are very, very consistent across. I would be surprised to see if there was a significant difference. And so we have done the means, and so now we can go back in and we can look at a one-way ANOVA. So we're going to look at here is mom's education as the factor, which is the independent variable, and the dependent variable we're looking at is vocabulary. We're going to go ahead and click OK there. And so this is our one-way ANOVA. It looks quite different from the within subjects ANOVA. You can see that the table is so much simpler, but it's a completely different test, so probably not too surprising. Going back into our write-up, I'm going to go ahead and put this table right here so we can see everything. I'm going to go ahead and write this up. We examined whether mom's education level was associated with kids' vocabulary at 18 months of age. So I'm being careful to use this word associated because we didn't manipulate this, so we don't want to say whether or not it caused differences. We're just going to say associated. And we're going to say that there was no evidence for a difference in vocabulary among the kids with, there's no evidence for a difference in vocabulary. I'm going to change this. There was no evidence for a difference in kids' vocabulary depending on mom's education. I'm going to report this as an F test again. We see it's here. So this is a between subjects, so we'll go with the between subjects line, right? Because these kids either have a mom who went to high school only, college, or completed some graduate training. And the degrees of freedom here are given on this side. And so we're going to go and type in 2 and 59. I'm going to go and say 0. And we have to round to 2, so this is actually a 1.0. P equals 0.91. And then we're going to, even though it's not a significant test, we would like to present the means so people know what the vocabularies were in these different groups. We would say, but unlike in the previous case where the overall F test was significant, which tells us that some group is different, here the significance overall F test is not significant, so we don't have to do any further exploration. All of these means are not going to be statistically different from each other. They're all going to be no difference. So we don't have to belabor the point and report all of these. We just leave it like this and we say kids, there was no reason to believe that kids who had moms with high school, college, or graduate training differed in terms of their vocabulary. Something like that, right? So there's no reason to believe that kids who had moms with high school, college, or graduate training differed in terms of their vocabulary. But we like to put those means in. So when we say what these groups were, we can go ahead and type in the means. So 13.17, comma, space, italics, uppercase SD equals 4.49. I'm pulling this information from this means table that we had requested. And I'm going to be lazy again. I'm going to highlight this so that I don't have to reformat this all the time. I'm going to change this to 13.60, 37, or graduate training. Put this here. 13.73 and 0.65. Great. And again, these write-ups you can write in a number of ways. You could say there was no reason to believe that kids who had moms with high school, college, or graduate training differed in terms of their education. And you could just, if you wanted to, you could just take this part of this sentence, which is the overall F-test, and report the F-test there, and just leave it like this. So we would just have this. A description of what happened. We examined whether mom's education level was associated with kids' vocabulary. There was no reason to believe that, and the F-test. So this is another example where you can have lots of different ways that you can write this thing up. I usually like it that right before the test statistic gets written up, there's a description of what it is we're going to be testing in plain English, and then the description of the result after that. Okay? All right, please go through this. It might be good practice for you, for instance, to go into the database and to look at, well, are there differences by education for vocabulary at 36 months? Maybe all kids are bound to learn an average of 13 words by a year and a half, but maybe the differences and the effects of mom's education really takes hold after the kid is much older. I can imagine a case that would be that would happen. The one other thing I wanted to talk to you about, which I put a pin in, I totally forgot to talk about, was in this within subjects test that we had run. Right, so we pulled our results from this table when we did the write-up for the previous test, that within subjects test. One thing I wanted to show you is that there's this evidence for this quadratic effect. So remember that these means went from, what, 14, where are our means? From 13 to 58 to 54. And what this quadratic effect tells us, and this linear effect, is that there's evidence that if we were to plot this out, I can do that actually. Going into Excel here, and I'm just going to type up these means. So 18 months, 24 months, 36 months, and at this time point, I'm going to say 13.42, 58.47, 544.62, and this top set of cells just corresponds to the condition, 18 months, 24 months, 36 months, and these are the mean vocabulary. And I want to, just for curiosity's sake, create a little graph of that. Oops. Insert a chart that looks like this. Okay? And so here's our different time points, 18 months, 24 months, 36 months. And we can see that there's a linear trend. Is that a statistically significant linear trend? That is, as kids get older, do they learn more in terms of their vocabulary? Well, this test up here tells us, yes, there is a linear effect. You can see that if we were to connect the dots between line 1, the average of this 18-month and this 36-month, there would be an upward trajectory. Kids' vocabulary gets larger. This quadratic tells us, is there a curve in this? And we can see that it's statistically significant. So there's evidence that there's a quadratic effect here. And that's being driven by the fact that at 36, their vocabularies really take off. So the difference between this and this is significant, but the difference between this and this is huge. So we get this exponential growth. And that's what is being given to you in this quadratic. I just thought that was interesting, maybe something that some of you might be interested in following up with. Anyway, as I was saying, I would recommend that you maybe go into this data set, play around with it a little bit, and please email me if you have any questions.